Welcome! Let's delve deeper into the fascinating hunt for those solitary worlds that roam the cosmos unbound by any star's gravity, the free-floating or rogue planets. Unlike the familiar planets in our solar system, these are cosmic nomads, drifting through the interstellar medium in perpetual darkness, making their detection a significant astronomical challenge. Finding them requires clever techniques that don't rely on the light of a host star because, by definition, they don't have one. The most successful strategy we currently employ to find these elusive objects is built upon the principles of gravitational microlensing, a subtle yet powerful effect predicted by Albert Einstein. Imagine a distant star, millions or even billions of light years away, serving as a luminous backdrop. As a massive object, such as a free-floating planet, drifts through space, and its path happens to align almost perfectly with our line of sight to that distant background star, its gravity warps the fabric of space-time around it. This warped space-time acts like a lens, bending the light rays from the background star as they pass by the rogue planet. This bending of light doesn't create a second image of the star that we can easily see, especially for an object as small as a planet. Instead, it causes a temporary magnification of the background star's brightness. As the planet moves into alignment with the star and then out of it, the star appears to brighten gradually and then dim back to its normal luminosity. This characteristic rise and fall in brightness over time is called a microlensing event, and the specific pattern of the light curve, how the brightness changes, provides clues about the mass of the lensing object. For a free-floating planet, which is far less massive than a star, the microlensing event is typically quite brief, lasting from just a few hours to a couple of days. In contrast, a star passing in front of another star would cause a much longer and more pronounced brightening. Detecting these short, faint blips in stellar brightness requires continuous, long-term monitoring of vast numbers of stars. Large-scale survey projects like the Optical Gravitational Lensing Experiment, OGLE, primarily using telescopes in Chile, and the Microlensing Observations in Astrophysics, MOA project based in New Zealand, have been observing millions of stars for years, patiently waiting for these rare alignment events. When a potential microlensing event is detected, other telescopes are often alerted to make follow-up observations to confirm the signal and gather more data. The challenge with microlensing is that it's a one-time event. Once the planet and the background star are no longer aligned, the magnification is gone. It's also a random process relying entirely on chance geometric alignments. This means we can't point a telescope at a specific spot and expect to find a rogue planet. We have to constantly watch large swathes of the sky and hope something drifts into view. Furthermore, microlensing primarily tells us about the mass of the lensing object. While we can infer it's likely a planet based on the duration and shape of the event, distinguishing it from a star or brown dwarf, microlensing alone doesn't give us information about the planet's size, composition, or whether it might have an atmosphere, or even moons. The scientific motivation for undertaking this challenging search is significant. The existence and abundance of free-floating planets can tell us a great deal about how planetary systems form and evolve. Current theories suggest that some rogue planets might be formed in the swirling disks of gas and dust around young stars, just like regular planets, but are then ejected from their parent systems due to gravitational interactions with other planets or the star itself. Others might potentially form in isolation from smaller clouds of gas and dust that don't coalesce into stars. By estimating how many free-floating planets exist compared to planets orbiting stars, we can gain insights into which of these formation and ejection mechanisms are most common throughout the galaxy. Estimates of the number of rogue planets vary widely, with some studies suggesting they could be more numerous than planets bound to stars. If true, this would have profound implications for our understanding of planet formation and the sheer number of planetary bodies drifting through the galaxy. Future missions, such as NASA's upcoming Nancy Grace Roman Space Telescope, are specifically designed with powerful microlensing capabilities that are expected to significantly increase our detection rate of free-floating planets, providing a much clearer picture of their population. While microlensing is the most promising avenue, astronomers continue to explore other possibilities, however speculative. Could a young, still warm rogue planet be directly imaged by extremely sensitive infrared telescopes? Perhaps, but they would be very faint and hard to distinguish from background noise. Could a rogue planet passing close to our solar system be detected by its gravitational influence on Oort cloud objects? Possibly, but such close passes are likely very rare. In essence, finding a rough planet in the sense of a starless wanderer is a testament to astronomical ingenuity, relying on the subtle ways these dark objects bend the light of more distant stars. It's a search that highlights the hidden nature of much of the universe and the powerful tools, both theoretical and observational, we use to uncover its secrets, one brief flicker of magnified starlight at a time.